So in this lecture, we will see three topics: salt balance, reclamation of saline and alkaline soils, and leaching requirements. Why we are discussing these topics in drainage engineering is because before doing drainage, we should know whether the soil is saline or alkaline, because a particular amount of alkali, salinity, everything is necessary for our crop. Okay. Other than when it is over a limit, then it may cause harm to the crops. So we have to just know whether the salinity is okay or the alkalinity is okay for the crops before drainage. So these are the main, so because of that we are discussing these topics in drainage. So we have to know the salt, amount of salt which is present in the soil, the reclamation, if the salt is excess, how we can remove that amount of salt and alkali from the soil, and the leaching requirement, how much amount of water is required for removing that salt. So all these things we have to discuss. As you all know, salinity refers to the concentration of salts in water or soils, and there are three types of salinity: primary, secondary and tertiary. Primary is otherwise known as natural salinity, secondary is known as dryland salinity, and tertiary known as irrigation salinity. The natural salinity may be caused by these reasons: rainfall, weathering, aeolian deposits, connate salt and saltwater intrusion. When there is a certain amount of salt in the atmosphere, when rain comes, the salt dissolves in the rainwater and it will raise the soil. It will make the soil saline. So that is the first reason. Second thing is weathering. When the parent material or the rock contains some amount of salt, weathering is actually the process of production of soil from rocks. When the rock itself contains some amount of salt, then the soil may contain, or soil also contains the same amount of salt. So that is the second thing. Aeolian deposits means wind may pick up the salt from one area to another area, and that is aeolian deposit. So some new areas, some areas which were not saline will become saline due to the wind. Connate salt, deposition of this salt content from the marine deposits and all, and that salt may sediment or accumulates in some areas, which causes salinity to the particular soil. Salt water intrusion is another reason. Salt water in coastal areas, salt water may intrude into the land surface for causing it saline. So these are the main reasons for the causes the causes of primary salinity. Secondary salinity is mainly caused due to the groundwater rise. In dryland areas, the temperature will be less, temperature will be higher, so the water content of the soil will be lesser. So groundwater have a capacity or ability to move up or rise up. Okay. Due to the upward movement of the groundwater, along with the groundwater, it will dissolve some salts in the soil and it will bring the salts to the topsoil. That may cause the soil saline. Third one is tertiary or irrigated salinity, which is caused by irrigation, process of irrigation. When the irrigation water contains some amount of salt, and if you are recycling the same water, then that kind of salt or that process may cause acid salinity in the soil. So the reasons can be sum up into 4 points. One is due to parent rock, seawater intrusion, irrigation water and groundwater rise. Due to these four reasons, mainly the soil becomes saline. And the salinity is a measure of the concentration of all soluble salts in water and is usually expressed as electrical conductivity. So electrical conductivity of the soil is the measure of salinity actually, because when there is a more amount of salt in water or soil, it can conduct more electricity. So electrical conductivity has a real correlation with the salinity of the soil. Actually, it is measured by means of the saturation extract from the soil. We cannot directly measure the electrical conductivity of the soil. So what we are doing is, we will saturate the soil first. We will fill all the pores of the soil with water. And after that, we will extract that water from the soil. And we will measure the electrical conductivity of the saturation extract. That water is known as saturation extract. We will measure the EZ of the saturation extract. That will give the direct value of EZ of the soil. Okay, that is how we measure the EZ of the soil. We will measure the electrical conductivity from the saturation extract of the soil. and it is measured by using EC meter, an instrument known as EC meter. Mainly the unit used for representing this EC is millisiemens per centimeter or decisiemens. Siemens is a unit of EC. Okay. Earlier the unit of millimole was used. Now it is converted to decisiemens. Okay, that is a standard unit. And the electrical conductivity of a soil extract from a saturated paste, when it equals or exceeds 4 decisiemens per meter at 25 degrees Celsius, the soil is said to be saline. As per USSL, United States Soil Survey Organization and all, as per their concern, the electrical conductivity of a soil extract from a saturated paste should not exceed 4 centimeter, 4 decisiemens per meter. Then it will become saline. When it is greater than 4, it is saline. Okay, as per USSL. And soil that contain a harmful amount of salt are often referred to as salty or saline soil. Here you can see that in this figure shows the salinity caused by salty irrigation water. If you are irrigating the soil with salt water, then it will cause the salinity of the soil in this area. And this one is salination caused by groundwater table rise. When the groundwater table rises, this is the groundwater table. When it rises, it will bring the salt to the top of the soil, which the water will get evaporated and the salt will remain above the surface of the soil. So this can also cause salinity in soil. Now, as per USSL, the soil is classified into 3 classes based on the salinity or electrical conductivity. When the electrical conductivity is greater than or equal to 4, ESP is another term which is used in coordination in relation with this salt and salinity and all. ESP is exchangeable sodium percentage, that we will see in the upcoming slides. When it is less than 15 and pH is less than 8.5. pH represents the acidity of the soil. ESP represents the alkalinity of the soil, alkaline presence of the soil. ESP means exchangeable sodium percentage, and EC is the electrical conductivity of the saturation extract. So this shows the salinity of the soil. So salinity, alkalinity and acidity. When it is greater than 4, it can be said to be saline. ESP is less than 15 and pH is also less than 8.5. When it is greater than 4, EC is greater than 4 and ESP is also greater than 15, then the soil is said to be saline sodic. Sodic means it is alkaline. It is equal to alkalinity. When the EC is less than 4 and ESP is greater than 15, we can say that it is sodic soil. Sodic soils or alkaline soil. Okay. So this is the case. And if the saturation extracts contains less than 3 grams of salt per liter, then the soil is said to be non-saline. So this thing is again represented into this. If the soil has 0 to 4.5 millimoles per centimeter of salinity, then that soil is said to be non-saline. If the salinity is greater than 18 millimoles per centimeter, then it is said to be highly saline soil. So gram per liter also the quantities are given here. You can check this and study. Another some related terms to the soil salinity are ESP, pH, SAR, etc. So what are these terms represents? ESP means the exchangeable sodium percentage. It represents the alkalinity of the soil, because here we have categorized the soil into 3 categories based on the EC, ESP and pH. So we have to see what is ESP. ESP is the exchangeable sodium percentage. It is the amount of adsorbed sodium in the soil expressed in percentage of the exchange capacity in milliequivalents per 100 gram of soil. So the soil may have the cation exchange capacity. Okay, some charges may be there. It has the capacity to exchange some cations. Okay, so how much is the capacity of the soil to exchange sodium to the capacity of the soil to exchange any cation? Represents the exchangeable sodium percentage. It is the ratio of exchangeable sodium content to the cation exchange capacity into 100. Both are expressed in milliequivalents per 100 gram of soil. So this term is known as the exchangeable sodium percentage. It should be when it is greater than 15, the soil is said to be sodic. When it is less than 15, the soil is said to be non-sodic or not sodic. Another thing is SAR. SAR represents the sodium adsorption ratio. So it is particularly for sodium. It is also representing the alkalinity of the soil. So SAR is the sodium adsorption ratio. It represents the ratio of sodium ions to the calcium and magnesium ions in soil. Na plus ions, concentration of Na plus ions, this square bracket shows the concentration. Concentration of Na plus ions divided by root of calcium ion concentration plus magnesium ion concentration divided by 2. So this is the equation for sodium adsorption ratio. ESP is a time consuming process. For finding ESP is a time consuming process. So we can use the SAR. SAR is a very quick process for finding the alkalinity of the soil. So this can be taken as another important thing. So this is a conversion of ESP and SAR. You have to just rate that. Another important term is pH, which represents the acidity of the soil. pH is the negative logarithm of hydrogen ion activity. So when hydrogen ion is higher, we can say that pH is higher. Okay, hydrogen ion is higher, pH is higher. So the soil is said to be acidic. Okay. So it is used as the index of acidity or alkalinity of the soil. So these are the terms which are related to salinity. ESP, SAR, pH, etc. Okay. And crops and saline soils. How the crops grow in saline soils. When the salt concentration is in the soil is very higher, the plant cannot grow healthily. Okay, it is harmful to the plants. So that is a main thing which you have to note. There are different types of crops which are according to the sensitivity of the crops to the salt content. The crops are divided into three. Highly tolerant, which can grow in any amount of salinity. Moderately tolerant, which can grow in some moderate amount of salinity, and sensitive crops which cannot grow in a single or smaller amount. Even when a smaller amount of salinity is there, it cannot grow. So red clover, peas, beans, sugarcane, pear, apple, orange, prune, plum, almond, etc. cannot grow in saline soils. Wheat, tomato, oats, etc. can tolerate some amount of salinity, and date palm, barley, sugar beet, cotton, asparagus and spinach can grow in very high saline soils. The limit of sensitive group is about 2.5 gram per liter of salinity. So above 2.5 gram per liter, this crop also cannot grow in saline soils. Okay, that is the thing. Now, how to reclaim? Actually, from the above slides, we got that some plants cannot grow in the saline soil. Most of the plants cannot grow in the saline soils. So, how can we remove the salinity? There are some methods for removing the salinity. So, that methods are known as reclamation methods. Reclamation of salt affected soil. How can we do that? So, we can consider the soil are of four types. Okay, first one is the saline soils with efflorescence of salt at the surface. We can see the salt content. When the soil containing salt, we can see the salt content by our naked eyes. White patches of salt are there. In such kind of soil, what we have to do is, we can scrap the surface of the soil. There are some salt content over the soil. So we can scrap off the salt content from the surface of the soil. And the second method we can use is we can leach. Leaching means removal of salt by flushing water through the soil. When we are flushing water over the surface of the soil, this salt will get dissolved in the water and it will penetrate or infiltrate down the soil and it will reach the groundwater and all. Okay, so that will happen. So in that case also salt is removed. So these two methods can be done for this efflorescence of, if the efflorescence of salt are present over the surface of the soil. Now, for soils with high concentration of soluble salts in greater depth with deep water table. Water table is deeper. Okay, water table is very much below the ground surface, and but the soil above the ground surface have some amount of soluble salt in it. In that case, what we have to do? We can do these methods. Leaching can be done. Surface or subsurface drainage can be done. Adoption of appropriate agronomic and cultural practices. Some what is that? Some chemicals can be added for removing the salt. Excess water can be added. Some irrigation methods can be chosen for removing the salt. So all these methods can be used for removing the salt content. The third case is soils with high concentration of soluble salt in greater or higher water table. Water table is very much nearer to the ground surface, and there is a high concentration of salt in the soil. In that case, what will happen is, when the water will touches the root zone. Okay, water will be very much nearer to the root zone. In that case, what we have to do is, first we have to lower the water table by pumping or by subsurface drainage, and we can do some other methods also. We can grow crops based on their sensitivity to salt. So when there is much salt in the soil, we have to grow the salt, the plants which are sensitive, which are not sensitive to plants, I mean salt. Okay, such kind of crops have to be grown. Very much tolerant crops have to be grown in such areas. Monitoring, maintenance and corrective measures can be done. So these are the methods by which we can remove the salt from this kind of soils. Another one is for soils with high concentration of soluble salts in, I'm sorry, this is actually for coastal areas. Coastal areas, what we can do is, this thing is not for a high concentration of soluble salts. For coastal areas, we can construct suitable embankments. Okay, suitable embankments or suitable walls can be constructed with one-way gates to stop the ingress of seawater to land. For restricting the seawater to the land, we have to construct some embankments in coastal areas. So these are the methods by which we can remove salt content of the soil. And the important method which we have discussed for removing the salt content is leaching. So what is leaching? Leaching means we are providing excess water for removing the salt content of the soil. What we are doing is, more water is applied to the field than is required by the crop. The additional water, what it does, the additional water will infiltrate into the soil. The water percolate through the root zone, and during percolation, what will do, the water will take up all the salts in this area, and it will move down below the root zone. And after that, we have to provide a subsurface drainage system. So the dissolved salts along with the water will reach the subsurface drainage system, and it will be delivered to a proper outlet. So this is how we can remove the salt content of the soil. We are providing excess water. The water will dissolve all the salt content, and it will reach the subsurface drainage system, and it will be effectively delivered to an outlet. So this is how we will remove salt by means of leaching. Now there is a term regarding this leaching that is known as leaching requirement. Before that, we have to see what is leaching fraction. Leaching fraction is the fraction of irrigation water needed for the removal of excess salt from the soil. So this fraction can be represented by two ways. One is electrical conductivity of the irrigation water divided by electrical conductivity of the drainage water. Irrigation water electrical conductivity divided by electrical conductivity of drainage water will give the leaching fraction, or the depth of drainage water divided by the depth of irrigation water. So these are, you have to just study these equations. In numerator, here the irrigation water is there. Here in numerator, drainage water is there. Electrical conductivity of irrigation water means how much salt is there in our irrigation water. We are providing the irrigation water, and the salt in the soil will dissolve in that. Now we are draining the water. So what will happen? The electrical conductivity of the drainage water will be higher, right? When there is salt in the soil, the electrical conductivity of drainage water will be higher. So this fraction will give the leaching fraction, or this also will give the leaching fraction. Now leaching requirement is equal to leaching fraction into total amount of irrigation water applied. The total amount of water required to bring the soil salinity from an initially high value down to an acceptable value in accordance with the salt tolerance of the crop to be grown is known as leaching requirement. The excess amount of water which is needed for removing the salt content of the soil is known as leaching requirement. It can be expressed by using this formula: E minus P into Ci divided by F into CFC minus Ci, where Ci is the salt concentration in irrigation water, CFC is the salt concentration in field capacity, soil at field capacity, and F is the leaching efficiency. E and P are evapotranspiration and precipitation. So this is the equation used. P is effective precipitation, which is used by the root zone of the crop. So this is the equation used for finding the leaching requirement of the crop. Now another important thing we have to see is salt balance in soils. How the salt will get balanced in the soil. So this figure shows the water balance actually. Okay, there is a plant. A plant will take up the water from the root zone and it will transpire. The transpired water will get precipitated downside, and some of the water will be taken by the plants again. The remaining water will be depercolated. Again, in order to compensate this depercolated water, the capillary water from this water table will rise. Capillary rise will be there. This water is also taken by the plant. So this is a cycle. There is a balance between all these things. Okay, like that for salt also there is a balance. Okay, salt in the soil and salt in the atmosphere, all that have a balance. So what is that balance? So this is equation for salt balance. By reading this equation you can get the logic. Okay, irrigation water entering the root zone into its salt concentration. Irrigation water plus effective precipitation plus groundwater will give depercolation plus change in storage. So the input to the soil or input to the plant root zone is irrigation, effective precipitation and groundwater rise. So these are the input into the uh, plant root zone, and the output from the plant root zone are depercolation. Depercolation means water is moving down from the root zone. So depercolation is there. Change in salt content of the soil solution in the root zone. So these are the actually output is dp, depercolation. Okay, so the difference between these two terms will give the change in salt content in the root zone of the crop. So irrigation and its salt concentration plus effective precipitation and the salt concentration of the rainfall plus groundwater rise and the salt content of the groundwater minus depercolation and salt concentration of the depercolation water will give the change in groundwater, the change in salt content of the soil solution in the root zone. So this is about the balance, the input and output. Balancing of the input and output is known as salt balance. Now we will move on to the alkalinity. Alkalinity, you all know, there are some types of alkaline salts present in the soil. Mainly it is sodium. So it is otherwise known as sodicity. Sodium soils are those which have an exchangeable sodium percentage of more than 15. When ESP is greater than 15, we can say that the soil is sodic or alkaline, and it will adversely affect the plant growth. So this is the ranking of the soil according to the sodicity hazard. When ESP is less than 15, there is no much hazard. When it is between 15 to 30, moderate hazard is there. That means plants cannot grow much. When it is between 30 to 50, moderate to high hazard. Most of the plants cannot grow. When it is 50 to 70, very high hazard. None of the plants cannot grow. And when it is greater than 70, extremely high hazard. None of the plants can tolerate above 70 ESP. So this is the hazard of sodicity based on ESP. And how to reclaim this, how to reclaim the sodic soils, we how to remove the acidity or sodicity of the soil. We can remove it by mainly two methods. One is by using chemicals. Some chemicals can be added into the soil for removing the alkalinity of the soil. The other thing is leaching. So chemicals and leaching are the two methods by which we can remove the alkalinity or sodicity of the soil. The chemical amendments used for sodic soil reclamation are, what are the chemicals used for removing the salinity? They are soluble calcium salts like gypsum, calcium chloride, etc. can be added. Acids or acid forming substances can be added, just like sulfuric acid, iron sulfate, etc. can be added. Calcium salts of low solubility, for example limestone, etc. can be added. So all these methods can be used for reclaiming the saline or sodic soils. And gypsum is the mainly used chemical compound which is used for replacing this alkalinity in the soil. Okay, the chemical name of gypsum is calcium sulfate 2H2O. So we can see how this gypsum acts. The gypsum requirement, how much amount of gypsum is needed for removing the alkalinity of a particular soil is known as gypsum requirement. How can we calculate this gypsum required for removing the alkalinity? So there is a method for that. This method is explained here. It is a chemical procedure. 5 gram of soil is taken in a 250 ml conical flask. We are adding saturated calcium sulfate, that is gypsum, into it, 100 ml of gypsum into it. 100 ml of gypsum into it, and it is shaken well, and we are filtering the water through Wattman number 1 filter paper. After rejecting first few mls, 5 ml of extract is pipetted into a 100 ml flask of porcelain dish. The filtered water is taken in a porcelain dish and it is diluted to 25 ml, and 1 liter of ammonium chloride ammonium hydroxide buffer is added. The buffer means it is an indicator or buffer, and 3 to 4 drops of erichrome black tea indicator. It is an indicator, a colored indicator is added. So it is titrated against EDTA, ethylene diamine tetraacetic acid. And first, when we are adding all these things in this sample, then the color will be wine red. Color of the solution will be wine red. When we are titrating it with EDTA, the color changes to blue. Okay, that point is the amount of gypsum required. Okay, that EDTA, amount of EDTA is the amount of gypsum required for the particular soil for removing the alkalinity. So that is how we are finding the amount of gypsum required for removing the alkalinity of the soil. And the calculations are given here. Mainly this alkalinity is caused by two compounds. One is calcium and the other one is magnesium. Okay, so for calcium, for removing calcium, the amount is like that. Normality of EDTA, because we are titrating it against EDTA. Normality of EDTA into milliliter of the EDTA into 1000 divided by milliliter of saturated calcium sulfate solution taken for this particular titration. Calcium plus magnesium can be removed by using this equation. So the gypsum requirement can be written as calcium, this equation, minus calcium plus magnesium into 2. That is the total amount of gypsum required for removing the particular acidity, I mean alkalinity caused by calcium as well as magnesium. So that is the thing. Now we'll move on to acidity. It is not given in your lecture anyway. We have to see the acidic soil also. Okay, acidity is actually the amount of H plus ions present in the soil. It is the exchangeable H plus or Al3 plus ions present in the soil. According to the pH, it is represented by the pH of the soil. According to the pH, there are different acidity levels. When it is less than 3.3, it is ultra acidic. When it is greater than 3.5 to 4.5 it is extremely acidic, 4.5 to 5 it is very strong acidic, 5.1 to 5.5 it is strong acidic, and when it is again the acidity decreases when it is greater than 6. Above 7 it is alkaline. So this is about the acidity levels. The acidity may be also due to this rainfall, parent material, fertilizer use, plant root activity, decomposition of organic matter, etc. Climate, vegetation cover, topography, human interference, etc. Acidic soils may develop due to all these reasons. How can we reclaim this acidity? How can we remove the acidity of the soil? The acidity of the soil is mainly removed by means of a chemical known as lime. Okay, acidity means it is the excess amount of positive ions. So we have to provide some what is that? Some alkaline substances for neutralizing the acidity. Okay, so lime is the effective alkaline substance which can remove the acidity of the soil, and it is measured by using pH meter. Acidity of the soil is measured by using pH meter. And how can we calculate the amount of lime required for removing the acidity? So this is the procedure for that. 5 gram of air-dried soil is taken, 5 milliliter of distilled water and 10 milliliter of the extract in buffer are added. Stirred continuously for 10 minutes. We will find the pH. Now the requirement of lime is calculated from table values. So there is a table which is developed by a scientist for calculating the particular amount of lime for a particular pH. So first we will find the pH, and after that from the table we will take the amount of lime which is used for neutralizing the particular acidity. Okay. So this is how we will find the lime requirement. So this is about today's lecture. Thank you.